Hello. Hello indeed. So, new topic, topic, work and energy. Hope you're excited. And let's start. I've got some reasonably easy stuff for you today. So we'll start with the basics of what is work. And I'll try to expand on the definition of work that you're given in school. Okay. So, work in physics. Well, you probably know that if you have an object and you have a force acting on that object, and the object moves a certain distance, let's say it moves a distance s, we say that the work is force times distance. What's missing? What's missing? Time. Well, time doesn't matter. Doesn't matter how long it takes you. The work is force times distance. That's it. Who's managed to open the assignment and read part of it? Have you done work in school? Have you done the work topic in school? Not really. Okay. Well, imagine I have a car. Well, I do have a car. And I used to have a very small car. And sometimes just for fun, I like to push it around. So I just push the car and the car moves. Not very fast, but it does move. So if I pushed with a force of 50 newtons, for example, and the car moves 3 meters, then the work I have done is 150 joules. Okay, work done by me. Done by me. 50 joules. Does that make sense? It's very straightforward. This is what work is. Work is the amount of energy transferred. Work is energy transferred. So that means I have transferred 150 joules to the car. If there is no friction, that means that the car's kinetic energy is now 150. If no friction, then the car should have 150 joules of kinetic energy. Right? Does that make sense? So I'm starting very simple, very basic. Okay. Now, if there is friction, friction would reduce. Friction would do work against. Friction would reduce kinetic energy of the car. By doing negative work. But how can work be negative if it's force times distance? That's the missing piece. But how can work be negative? Once again, so what I'm doing is I'm pushing the car, so I'm giving it energy. Friction takes that energy away. Intuitively, you understand friction takes energy away. But how does it do it? It does it by doing negative work. What is negative work? Well, we are missing a very crucial bit of information because work, in fact, work is force times distance times the cosine of the angle between them, between force and displacement. So when I push the car, I'm pushing that way. That's my force. And the car is moving that way, S. What is the angle between F and S? 0. Very good. So work by me is force times distance times cosine of 0 degrees, which is, let's say this is what, 3 meters, and this is 150 newton. This is 50 newtons. 50 newtons. It's a very small force. It has to be a very small, very small car. Anyways, it's 50 times 3 times cosine 0 is 1, which is 150 joules. This is the work done by me. Now imagine there's a friction force here. Then let's say it's 20 newtons. Work done by friction. What's the angle between the friction force and S? The friction force and S. Okay, does everyone agree that it is 180? How many people today? 4. I haven't heard from Anne, Perchita, and Vishaka. What do you agree that the angle between friction force and S is 180 degrees? Okay, so it's going to be F friction, force of friction times the displacement times cosine 180 degrees. And cosine 180 degrees is -1. So it's 20 times 3 times -1, which is -60 joules. So friction does -60 joules of work, which means it takes 60 joules of kinetic energy from the car. So the car now has 90 joules of kinetic energy. Is that making sense? Ask me a question, please. I mean, doing work means pushing, and if there's movement, then okay. In fact, work and so force is a vector. Force is a vector, and displacement is also a vector. And work is this dot product, is the scalar product of SF multiplied by S. Scalar product. Okay. So, for example, if we can say that in this example, the example of the car, if we have the axes, like this is the x-axis, this is the y-axis. We have the force. Force is a vector, and the vector is 50, 0. And displacement is also a vector. Displacement is 3, 0. Then force dot s is 50, 0 multiplied by 3, 0 equals 50 times 3 plus 0 times 0, which is 150 joules. If you push something in a circle, the force has to change constantly. So you can't use this. Well, you can, but you can't use this. The force won't constantly change, right? Because if you're, otherwise it wouldn't be moving in a circle. We will get to that. Actually, there's one. I'm going to go through an example where you move in a circle. But yes, that's a very good point. Now, if the friction force is minus 20, 0, and the displacement is still 3, 0, then force of friction times S is going to be minus 20, 0 multiplied by 3, 0, and it's going to be minus 60 joules. So it still works. See, so you can do it as vectors, or you can do it as so these two formulas. So I would say forget about this one. These two formulas are equally valid. Okay. I mean, working with vectors doesn't make too much sense, so I'd say stick with the first one. Stick with the first one. Problem two, I kinda explained that already. When you do work on an object, you increase kinetic energy. When work is done, it increases kinetic energy of the object. That makes perfect sense. If I have a ball and I kick the ball, something I haven't done probably 5 years. I do like golf though. Okay, if I hit a ball, the ball moves, and there's a force, and the ball moves. So the work done goes into the kinetic energy of the ball. In fact, work is equal to the change in kinetic energy, and that is known as the work energy principle. Work energy principle. So is it work done in general or work done in a direction? Well, it's always work done in the direction of motion, because if you think about it, where does the cosine theta come from? Well, if you have a force, let's say force, and you're moving in that direction, if this is the angle between them, theta, if this is F, then you draw a right angle triangle, and this part, this is the projection of the vector. It's actually F cos theta. Because this is the adjacent side of a right angle triangle. It's F cos theta. This is F, and this is F cos theta. So, and the work is F cos theta times S, or F S cos theta. So in a way, it is done in the direction of motion. Okay, Vishaka is asking, is the work done in general or work done in a direction? Or is it after you consider force of vector quantity displacement? The work is a scalar. It is important to understand. These are vectors, but work is a scalar. It can be positive or negative. That's it. It doesn't have direction. Positive work. So work is a scalar. Positive work means increasing kinetic energy. Negative work means decreasing kinetic energy. Right, so when we want to slow something down. Okay, this is a very good example. So effect, motion, and forces. So if I have a box, let's make it fun, and I push it. If I push the box, you can see that the speed increases, so the kinetic energy increases. So I'm doing work increasing the kinetic energy of the trolley, of the box. If I stop pushing, the kinetic energy stops increasing. So we have kinetic energy. So you all understand what kinetic energy is, right? I don't need to explain that. At least intuitively, you understand kinetic energy, right? Kinetic energy is energy of motion. Now, if I want to stop the box, I have to push it in the opposite direction. And now the angle between the displacement is to the right and force is to the left, is 180 degrees. So the work, I'm doing negative work. So I'm removing kinetic energy from the box. And now I'm doing positive work because I'm pushing in the same direction as it is moving. So basically this means force in direction of motion. And this means force in opposite direction of motion. Exactly. The theta angle is the angle between the force and the direction of motion. Exactly. Okay. So kinetic energy is equal to 1/2 mv squared. Okay, and yeah. No, not necessarily. So there's a question: would the object move in a diagonal direction in this case? I need to explain the situation. So imagine you have a box and you're pulling it that way. There's still gravity. There's a gravitational force. So the box will not move in that direction, would it? Like, I mean, if you're pulling something along the rope with a rope, the box would move that way. The box would move in that direction, S. And this is a force. And this is the angle theta. So the work is force times distance. Well, technically can't do that. It's F times S. Or work is force times distance times cosine theta, which is the same thing. These are equivalent, right? So it's not always that you move in the direction of the force. There's also gravitational force here, right? Don't forget about that. There's a gravitational force which is down, mg. What is the angle between mg and s? So work done by the force of gravity. Cross products. 90, yes, there's a 90-degree angle between mg. So it's mg, the force, multiplied by s, multiplied by cosine of 90 degrees. And cosine 90 degrees is 0. So the gravity is not doing any work here. Okay. Work done by the gravitational force. If the resultant direction, of course, but we're talking about the work done by an individual force. Yeah, if you pull really hard, you won't lift it off the ground, of course. You have to compare the gravitational, the weight and the vertical component of the tension in order to answer that question. But that's, yeah, we'll get. That's not what we're talking about. Gravitational force. So consider a simple example. You have the ground, and you have a ball of mass m, and the ball moves down, falls down, and the distance that it falls is h. So the force is down, is the weight force, it's mg, and the displacement s is equal to h. And the angle is 0 degrees because they're in the same direction. So the work done by the gravity is equal to mg multiplied by h multiplied by cosine 0 degrees, which is mgh. Interesting. You've probably seen that formula before. If you pull the block with force direction with the block moving along the gradient of an exponential graph. I'd say no. Because an exponential graph, because at some point it will become straight. It will become like this. But an exponential graph will always go up, 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 up. It will always, the gradient of an exponential graph goes to infinity, but here you will get it to move in a straight line eventually. So I'd say no. That would be an interesting piece of maths to do, to find the trajectory. Okay, so if you move a ball falling down, a ball falling down, it's positive. This is positive. What does positive means in terms of kinetic energy? Work is greater than 0. It means kinetic energy is increasing. Makes perfect sense, doesn't it? A ball flying up. If the ball is flying up, through a height h, then you have the gravitational force mg and the displacement s. So work done by gravity is mg multiplied by h multiplied by cosine 180 degrees, because the angle between s and mg is 180 degrees. S is a vector, of course, mg is a vector technically. Yeah, so when I say mg is a vector, s is a vector. And it's equal to minus mgh. So work is negative, means kinetic energy decreasing. And that's very easy to check. You take an object, you throw it up, and as it goes up, kinetic energy decreases, and then it stops momentarily before falling back down. What if you don't move vertically down? What if you move from here to here, for example? And let's say this distance is s. And the gravitational force is mg. And displacement is s. And the angle between them is theta. So the work is force times s times cosine theta, which is mg s cos theta. But if you look at this distance h is in fact, because it's a right angle triangle, h is s cos theta, because this is theta, h cos theta, which is, so this is mgh. So even if you don't go in, if you don't fall down, then the work done is mgh. As gravity is negative, does this make gravity negative in all situations like Suad? Yes and no. It's a complicated issue. Look, let me finish this bit, and I'll say some words about gravity. It's important to understand. So straight path. What if it's a curved path? Well, let's say you're going like this. Well, you can always break down a curved path into straight sections. And for each section, the work is mg delta h, change in height. Because we've just proved, because for a straight section, the work done is mgh. So a curved path can be broken down into multiple small sections, and the overall work is, if this is h, is mgh, mg delta h, change in height. Okay. And this is also known as gravitational potential energy. Gravitational potential energy, gravitational potential energy, or GPE, is the amount of work gravity does if you move from point A to B. Amount of work done by gravity, if you move from A to B. So it's interesting that if you move from point A to point B, doesn't matter how the path that you take, the path that you take does not matter. The work done would always be the same. And the work done by gravity, does not depend on the path taken, and always equal to mg ha minus hb. So mg times change of height. Okay, so GPE gain, or change in GPE, which the GCSE formula that you should be familiar, change in gravitational potential energy is equal to mg change in height. And this is a very important formula. Now, gravitational potential energy. We say gravitational potential energy is mgh. But what is h? We say. But what is h? Is it the height above the floor? Because certainly, well, if I'm talking about my pen, I would normally talk about the height above the table. Height above table. Height above floor. Height above the ground. But even if you're on the ground, you can dig a hole. So h is an arbitrarily chosen reference point, as can be demonstrated here. Okay. So I have a skater. The skater when the skater is here, the kinetic energy is potential energy is 2,900 joules or 3,000 joules effectively. But that's above this reference point. If I choose a reference point differently, for example, if I choose the reference point here, I can see the potential energy is negative. It really depends where I'm measuring from. I can make the potential energy 0 if the reference point is here or here. It's the change in height that matters. So you could always choose a different reference point. We normally choose the reference point as the lowest point, as the lowest reasonable point. But you could always take it as the highest reasonable point, and then potential energy is going to be negative. Does that make sense? Everyone? Can I have a reply from everyone? Do you understand that the potential energy depends on where you're measuring from? And it's only the change that matters. So as long as you're changing, its height can be is the height above a chosen reference point. Yes, by measuring from, look at the total energy. The total energy is 3,000 joules. And when the skater moves, you can see that the total energy, well, let's do it like this. The total energy does not change. The kinetic energy increases, potential, but they switch potential to kinetic, kinetic to potential, kinetic potential to kinetic, etc. But the total does not change. If I choose the reference point differently, you can see that the total energy is 0 now, or almost 0. And if I release, you can see that kinetic changes to potential, potential changes to kinetic, but the total is still 0. So whichever reference point you choose, energy will be conserved, but that amount of energy that you choose it to have in the beginning. Energy is not necessarily a tangible thing that you can measure. Look, a simple example. I have a car which I've had since I was 7, probably. Okay. Toy car. And what's the kinetic energy of this car right now? Exactly. Well done, Luke. Where are you measuring it to? If you're measuring it relative to the Earth is moving. The Earth is moving around the sun at about 30 kilometers a second. So the car is traveling at approximately 30 kilometers a second. So it's a really, really fast car. It has a lot of kinetic energy relative to the sun. And if you take a relative to the center of the galaxy, the sun moves around the center of the galaxy, it has even more kinetic energy. So it depends what you're measuring from. It depends on your reference point. But whichever reference point you take, as long as it's an inertial frame of reference, it's the energy is going to be conserved. But the amount of total energy depends on where you're measuring from. That's just like that. Potential means it has the potential to turn into kinetic. The best way to understand it. I like to phrase it, it has potential to do harm. Okay? If an object has potential energy, if I release it, it has the potential to do harm. Chemical potential energy, yeah, chemicals have potential energy to do harm. There's a question. Because isn't the energy the thing you get and use when you burn bread, for example? Or I thought energy was a tangible thing, like there's some thousands of joules in the universe. Mass doesn't change based on the reference point. Mass does change based on the reference point. That's the thing. Einstein's special theory of relativity, mass increases if you move faster. So in different frames of reference, you would have a different mass as well. That's bizarre. Mass, as you will learn in the future, your mass is equal to the mass when you're stationary divided by square root 1 minus v squared over c squared. Yes. So your mass is your mass when you're stationary divided by 1 minus v squared over c squared, where v is your velocity and c is the speed of light. And if you move at speed of light, if v equals c, then m is what is m? If speed equals speed of light? Yes, Luke. Well done. You've ahead of the curve. It is infinity. This is infinity. So that means you can't move at the speed of light. Yeah, I mean, when we say the amount of energy in the universe is constant, we mean relative to any given reference point. We would like to take the center of the universe, but what is the center of the universe? Does it even exist? Aren't we in the center of the universe? Because I mean, we did start with the universe. The universe did start from a Big Bang, which happened right here. Right. Okay, so yeah, that's we can I can talk a long time about this, but let's stick to problem solving. Okay, you'll learn a lot about this. And mass being pulled. So let's do some problems. Is there something else I wanted to? Photons are massless. Yes. Well, we say photons have a rest mass of 0. So if photons could be stationary, their mass would be 0. But they're not stationary. So technically they do have mass. No, it doesn't work like that for photons. Problem 4. A mass being pulled along a level road by a rope attached in such a way that the rope makes an angle of 40 degrees to the horizontal. The force in the rope is 20 newtons. What is the work done by this force in moving the mass a distance 8 meters along the level road? So we have a mass, and there's a level road, and you pull the mass with a force at an angle theta, and the mass moves a distance s. The force is 20 newtons, and s is 8 meters, and the angle is 40 degrees. 40 degrees. So the work done by force by F, work F is equal to force times S times cosine theta, which is 20 times 8 times cos 40, which is approximately 20 times 8 times cos 40, or 123 joules. Imagine for a second that, well, let's imagine that there's a weight which is, let's say, 4 newtons, and there is a normal reaction force. No, weight 4 newtons, that's not possible. 40 newtons. So imagine it's 4 kilograms, the weight. Work done by the weight force, mg, by mg. Panic. By mg is equal to force times mg times s times cos 90 degrees, remember? Because it's 90 degrees, so it's 0 joules. So gravity does not do any work. Now the normal reaction force, we don't know the normal reaction force. We could calculate it. It's not 40 because you're pulling it up. We don't know the reaction force, but we know that the work done by the reaction force is equal to reaction force times S times cos 90 degrees. Again, it's 0 joules. Whatever R is, well, R, in fact, is going to be 40 minus F sine 40. So it's approximately 40 minus 20 sine 40, about 27 newtons. Okay, so it's approximately 27 newtons. It's not 40 because we're pulling it up, right? I hope you understand that. And imagine there's a friction force, and let's say it's a 10 Newton friction force, F of friction, work done by the force of friction. So work by friction is force friction times S times cos 180 degrees. The force of friction is 10 times 8 times minus 1, which is minus 80 joules. So total the total work done is 43, well, it's 123 joules plus 0 joules plus 0 joules minus 80 joules, which is 43 joules. So the change in kinetic energy of the box is 43 joules. And if we know the kinetic energy, we can calculate the velocity, right? Because we know that it's a, what's the mass of the box? Who can tell me what's the mass of the box? 4 kilograms, well done. The mass of the box is 4 kilograms because the weight is 40. So 1/2 mv squared is 43. So we can work out v is 43 times 2 divided by m square root, which is 43 times 2 divided by 4 square root. It's 20 square root of 21.5, which is 4.6 meters per second. That's how fast the box will move as a result of us pulling. So the answer: total work is 43 joules. Change in kinetic energy is also 43 joules because that's what change of work does. And the final speed is 4.6 meters per second. That's how fast the box moves. All right, let's have a look at circular motion. Okay. Now this is the sun, and this is planet Earth. And if this is the velocity, and this is the gravitational force on the planet. And when I press play, you can see that the Earth goes around the sun. The force is constantly changing. Yeah, because force is constantly changing, but the angle between what's the angle between the movement and the force? This is the force. This is the movement. 90 degrees. But what is the work done by the gravitational force? Zero joule. Does everyone understand? The work done, that means that the change in kinetic energy of the planet is 0. And that means that the speed is constant. Yes, because work is the change in kinetic energy, right? If there's no work, there's no change in kinetic energy. How much sense does that make on a scale of 0 to 10, please? Okay, let's get a vote. I see one person left. Okay. Lovely. Now, let's imagine that we've reduced the speed of the planet twice. Okay. Now this happened because this is a not to scale diagram. Okay. The sun and the earth are not really that size relative to each other. Let's do it to scale. Now you can see the star and the planet are tiny specks of dust. This is what they actually are. So the star and the planet, they're actually very, very small. Okay. And if I reduce, if I go normal, that's how it goes. You can't see the planet because it's just too small, and you can't see the star because it's too small. But this is the same thing. Gravitational force, velocity. I'm going to restart, but this time I'm going to reduce the speed of the planet twice. Okay, don't need the grid. Don't need the gravitational force yet. This is what we see with comets, for example. Comets go in elliptical orbits. Why do they go in elliptical orbits? Because you need to move with a very specific speed in order to go in a circle. So if I were to double the velocity back to the original, when the planet is here, I won't go back to a circular orbit. If I go any faster, it will be elliptical. If I go any slower, it will be elliptical. If I go a lot faster, then it won't go parabolical. Parabolical means it will never return. But if I halve speed, it's going to be an elliptical orbit. Yeah, so now if you remove the grid, right, so in this position, the force, this is a 90-degree angle. So when it's in this position, the work is 0. Now, when the planet is here, it is moving like this. And when the planet is here, it's moving like this. And when the planet is here, it's moving like this. But the gravitational force is always in that direction. And this angle, theta, is less than 90. And that means that the work is positive. So what does that mean to the kinetic energy? As in this position, the kinetic energy is increasing. here, the force is in that direction. The force is in that direction, and the angle, theta, is greater than 90 degrees. That means that the work is negative, and that means the kinetic energy is decreasing. Let's see. Here, the force is that way. Not to scale, of course, because it's going to be bigger. But the angle is 90 degrees again, so work is 0. So here, kinetic energy is maximum. And here, kinetic energy is minimum. Let's watch it again. So velocity and gravitational force. You can see the gravitational force increases as it gets closer. But the important thing is the angle. Look, the angle here is less than 90. So now it's speeding up. The planet is speeding up. So if I draw this on this section, it's accelerating. And on this section, it is decelerating. Yeah, because if you remember cosine, the cosine graph, theta, cos theta, this is 0 degrees, this is 90 degrees, this is 180 degrees. So it's positive and then negative. 1 minus 1. Negative, positive, negative. When it's positive work is done, kinetic energy increases. Okay, so change in kinetic energy is positive, and here change in kinetic energy is negative, slowing down and speeding up. Hope you like that. And for a circular orbit, kinetic work is 0, so kinetic energy does not change, speed is constant. And coming back, so you can see that the speed is increasing fast, slow, 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 faster, 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 fast, super fast, slow, 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 slow. You can definitely see the speed changing as it goes round. Any questions? Problem 6. Find the speed of the mass at the end of a pendulum of length 1 meter that starts from rest at an angle of 10 degrees from the vertical. Well, if you take a pendulum, where's my pendulum? You take a pendulum and release it, it will have kinetic energy at the bottom. Well, it will have kinetic energy the moment it starts moving. Now it has potential, and at the bottom it has kinetic. Potential, kinetic, potential, kinetic, potential, kinetic, etc. So the task is to find how fast it will move at the bottom of the swing. Okay, so here at this part it has potential energy only. The potential energy is mgh. At the bottom is kinetic only. There's no potential energy. So it means it has 1/2 mv squared, right? Because here v is 0 and here h is 0. So it's at the bottom of the swing. So all the potential, so we have potential energy, gravitational potential energy, turning into kinetic energy, and then back into gravitational. So we can say that mgh is equal to 1/2 mv squared. However, we're not given h, we don't know h, but we do know that this is 1 meter, and we know that this angle is 10 degrees. Okay, well, this is L, if this is 1 meter, we can say, okay, this is a right angle triangle. This angle is 10 degrees. Can we find this side? What is this side in terms of L and theta? L cos theta. Does everyone agree? Does anyone disagree? This is a right angle triangle, and this side is equal to L cos theta. But we also know that this side is L. So what is H? In terms of L and cos theta? What is H in terms of L and L cos theta? Well done. It's L minus L cos theta. Do you see that? Does everyone understand why H is L minus L cos theta? Give me a vote on a scale of 0 to 10, please. Okay, very good. So we can simplify that. L 1 minus cos theta. And now we sub that in. So that's going to be mgl 1 minus cos theta equals 1/2 mv squared. Now you probably notice that m cancels. I multiply everything by 2, so 2gl 1 minus cos theta equals v squared. So v is equal to the square root of 2gl 1 minus cos theta, which is square root of 2 times 10 times L, which is 1 meter, times 1 minus cos 10 degrees, which is approximately, so you just sub that in, so square root 20 times 1 minus cos 10, okay, 0.055 meters per second. That's it. Okay. A mass m hangs vertically at the end of a string of length L. A force F is applied to the mass horizontally, so that it slowly moves to a position distance h higher than before. What is the work done by the force F? Now, you might be tempted to find this distance and then find the angle and then say this is the force, this is the displacement, this is the angle between them, let's call it delta, and say work is force times S times cos delta. The problem here is that this force is not constant. At the beginning, you only need a very small force to get it to move. As you push further and further, this force has to get bigger and bigger and bigger. You probably know this if you've ever played with the swings. If you want to push someone a little bit on the swing, that's fine. But if you want to push them all the way to the top, that's almost impossible. You can't do it in one go. It gets really, really tough. Right? Do you understand what I'm talking about? Right? If you just start pushing someone on the swing, it's very easy. But as you push further, it gets harder, harder, and harder. So that means that the force has to change. Well, one way, which you could do potentially, is you could say that if we move a tiny little bit, the force doesn't have enough time to change, and that would be work is equal to an integral of F cos delta ds. That would be a massive problem because first of all, you don't know integration yet. Or maybe you do, but I'm not expecting you to. Okay. And secondly, even in year 13 A-level student would probably struggle with that. I'm sure they would. I would struggle with that, honestly. It would take me a good half hour to solve that. So yeah, that's not a very good method. It's not to do integration here. Well, what you need to do here is say, well, look, if we're moving really, really slowly, we can assume that there's no change in kinetic energy. We can assume that kinetic energy at the start is equal to the kinetic energy at the finish, and it's zero. It's just lifting. So the work done there's no change in kinetic energy. So the work done by F plus the work done by gravity must be zero. So change in kinetic energy is the work. So change in kinetic energy is the total work. Change in kinetic energy is the total work. Work is zero. So there are two forces doing work. There's the mg force doing the work, and there's the F force doing the work. And we know the work done by mg, well, it's equal to the change work done by the mg force is equal to change in gravitational potential energy is equal to minus mgh. So the work done by the force F has to be plus mgh. That's it. Okay, we haven't taken work done by T. Work done by the force T. What is the work done by the force T? What if you're moving in that direction and T is in that direction? What's the angle between T and the movement? 90 degrees. So the work done by T is 0. It's always 0. The work done by tension is 0 because it's always perpendicular, always 90 degrees to movement. Okay, let me rephrase that. Using the work energy principle, so the change in kinetic energy is equal to the total work. So the change in kinetic energy is equal to the work done by the gravitational force, mg, plus the work done by the tension force, plus the work done by the force F. Because there are only 3 forces acting. The work done by tension, work done by mg, work done by F. We know that the change in kinetic energy is 0 because it's moving very, very slowly at constant speed. Moving slowly at constant speed. The slowly doesn't matter, moving at constant speed. That's what matters. So work done by mg, we know it's minus mgh because it's moving up against gravity. Plus the work done by tension is 0, and plus the work done by the force is what we are looking for, and that's equal to 0. So the work done by that force is equal to mgh. That's it. Do you understand this question on a scale of 0 to 10, please? Okay. Another point of view of doing work increases energy of an object. So we can say that work done is equal to change in gravitational potential, sorry, change in energy. So we can say that work is equal to the change in kinetic energy plus change in gravitational potential energy. Well, we're not changing kinetic energy, so that's equal to 0. So it's equal to change in gravitational potential energy, which is mgh. That's it. By doing work, we increase gravitational potential energy of the pendulum. That's what we do when we lift things. Yeah, if I take this, I do work lifting it above. Very simple point of view. So can I get a vote now? Does that make sense now? Is that a 10 from everyone? Or still a 9? Okay. So by doing work, I'm pushing it. So there are different points of view, which they all lead to the same reply. So this is not the way to go. So I started with this. This is not the way to go. So I'll just delete that, just not to confuse you. Okay, so oh wow, a lot of stuff today. I won't be able to do everything. What is the minimum speed of the mass is so that it makes over the barrier? So if it makes over the barrier, that means the smallest speed it can have at the top is 0. If speed at the top, speed at the top is 0. If it just makes over the barrier, so it's the limiting factor. So that means that here we have kinetic energy only, and here we have gravitational potential energy only. So we have 1/2 mv squared, that's the kinetic energy, equal to mgh, and m cancels. So v squared equals 2gh. So v is equal to square root of 2gh, which is, oh, that's it. That's the answer. That's the minimum speed that you need to go over the hill. And interestingly, the mass is not involved in here. Okay. Now, what is the minimum speed the mass must make to over to position B? Well, in order to make it to position B, it must reach A with a speed of 0. Well, just above 0. Greater than 0. Okay. So if it's here with a speed of 0, or very, very small speed, it can make it to B. At A, velocity is greater than 0. And that means that, and from the previous question, we know that this minimum speed for that is square root of 2gh, well, greater than 2gh, which is square root of 2 times 10 times h, which is 4. 8. Square root of 80 to 9. Square root of 80. 8.94. 8.94 meters per second. So it has to be greater than 8.94 meters per second to make it to B. If the speed is 12, what will the speed at A and B be? Okay, if the speed is 12, we can calculate the kinetic energy at the bottom. Kinetic energy is 1/2 mv squared. Let's call it mu squared. Oh, it's v. Okay, let's stick to v. And from here, it is still moving because it has more energy. So it has gravitational potential energy equal to mgh, and it has kinetic energy, which is 1/2 mv squared. I don't like u. I don't like v. v1 squared. va. Okay, that's the perfect way to do it. mgha. And here we have gravitational potential energy as well, which is mghb. And kinetic energy, which is 1/2 mvb squared. And because energy is conserved, we have the total energy at A, at the start, equals the total energy at A equals total energy at B. That means that the kinetic energy at the start equals kinetic energy at A plus gravitational potential energy at A equals kinetic energy at B plus gravitational potential energy at B. So kinetic energy at the start is 1/2 mv squared. Kinetic energy at A, so 1/2 mva squared plus mgha. Okay, comma, oh, semicolon. And 1/2 mv squared is equal to 1/2 mv b squared plus mghb. Okay, so m cancels again. You see, m doesn't really matter, and we need to find v. So multiply everything by 2. V squared is equal to va squared plus 2gha, which looks very similar to a Suvet equation. M is m is math. Okay, h, very good. Very good. So VA squared is V squared minus 2GHA. And VA is square root of V squared minus 2GHA, which is going to be square root of 12 squared minus 2 times 10 times 4. 144 minus 80, 64, square root of 64. Going to be 8 meters per second. Okay, so at A, it's going to be at 8 meters per second. And here it's 12 meters per second. And at B, VB, it's very similar. It's going to be square root of V squared minus 2GHB, which is square root of 12 squared minus 2 times 10 times 2 meters, 40, square root of 104, which is approximately 10.1, square root of 104, 10.2, okay, 10.2 meters per second. Okay, so interesting. So 10.2 meters per second. So it only decreases, the kinetic energy only decreases a small amount. So the speed, it only decreases a small amount in order to reach the top. Even though the minimum speed that you need is 9 meters a second. Yeah, just, this is surprising to me, okay? Well, I mean, it's not surprising when you think about it, because kinetic energy is proportional to v squared. That is the reason. The minimum speed is 8.94 meters per second. If speed is 12, then VA is 8 meters per second, and VB is 10.2 meters per second. It will speed up. And we'll do the rest in 2 weeks' time. Actually, maybe not. But yeah, I'll try. Oh, because you have 3 different positions. In any given position, kinetic energy, total energy is the same. Look. So here you have zero kinetic, maximum potential, and total is like this. When you're here, you have kinetic energy, you have potential, but the total is the same. Total energy here is still that. So total energy does not change as you go around the skate park. Yeah, you wouldn't add energy at A, energy at B, because then it doesn't make any sense. Okay. All right. You're welcome. See you next week for some maths.